Okay, now we're going to look at the bowling problem. The bowling problem involves a round object that is moving with an initial velocity v0, but it hasn't begun rotating yet. We'll say this one's initial angular velocity is 0. And so it's like a bowler who's thrown his bowling ball down the lane. The ball has landed and is sliding, but it's on a surface that has some friction. So there's a mu value there. That means the linear velocity is going to be slowed by that friction, but at the same time it's going to apply a frictional torque, which will increase the angular velocity until eventually it will be rolling fast enough to catch up to its own speed. At that point, it will then start to roll without slipping, and the torque that is both increasing the angular acceleration as well as providing friction, which reduces the linear velocity, that will disappear because then it'll be a static friction and we won't end up with either acceleration. Then it'll move with constant angular and linear velocity. So let's take a look at this. Again, the first thing we'll have to do is a dynamic analysis of both the linear and angular. This will look familiar to you. We've done this a couple of times in the last few videos. So first, the ball represented from a linear standpoint is just going to have a normal going up and mg down. And then, of course, it's got the frictional force going left. So the summation of forces in the x is going to equal ma. And the only force on it in the x direction is the frictional force, and it's negative, so that's ma. In the y direction, we're just going to get from this that the normal is equal to mg, and that, of course, produces that the frictional force is mu times mg, so we can plug that in here. So negative mu mg is equal to ma. I can knock off the m's, and the acceleration, the linear acceleration, as this guy slides down the lane, is negative mu g. Okay, now we'll do the rotational part of it. We're gonna basically hold on to that acceleration value. Okay, from a rotational standpoint, again, we need the whole object. It has a frictional force acting along its bottom edge to the left. It's also got its weight, mg, and the normal force, but because those both go through the center of rotation, they produce no torque. The only torque is produced by the frictional force. So the summation of torques equals I alpha, and that torque is positive because I'll call the clockwise direction positive. So it's the frictional force times the radius is equal to I alpha. We originally called this the bowling ball problem, so we're going to consider this to be a solid sphere. That has a moment of inertia of 2/5 mr squared. You could also do this with a ring or a disc, and the only thing that would change is you'd insert the correct moment of inertia times alpha. We can do some simplifying here. I'm also going to plug in the size of the frictional force, which is mu mg. So mu mg r equals 2/5 mr squared alpha. And a couple of things cancel. The mass goes away, and one of the r's cancels. So I can rewrite the acceleration. The angular acceleration now is going to be 5 mu g over 2r. Okay, and then we'll save that acceleration for just a second. Okay, so what we have is the angular acceleration, which will increase the angular velocity from 0 up to the value needed in order to be catching up with its linear velocity. At the same time, the linear acceleration will be decreasing this initial velocity again until it matches up with the angular velocity. Basically, these two guys are going to sort of move together until they reach that magic number. We'd love to know what that magic number is, but again, I can't find it from this because I lost the connection, the one we've been using for the last couple of days. The condition for rolling without slipping is that A equals alpha R. Well, that's not true in this case because these guys are definitely out of lockstep, at least right now. But they will eventually be in lockstep, and I know the condition under which they will be. It will basically be when the velocity, which is accelerating by this amount, gets enough time for the final velocity to be what the value needs to be in lockstep with its angular velocity. The angular velocity, meanwhile, will increase from its 0 value of omega naught plus alpha t. Now, ordinarily, these two relationships wouldn't have anything to do with each other, especially when they both have different rates of acceleration. Both the linear velocity and the angular velocity are accelerating right now. But I do know one thing. When they eventually reach this sort of quasi-equilibrium where it's rotating just fast enough for its linear velocity, I know v is going to be equal to omega r at that magic point. So I can use these two kinematic equations in this condition to sort of build a formula that'll tell me how long it's going to take for that to happen. So let's build that formula. This will be v naught plus at is equal to all of this times r. So omega naught r plus alpha r t. Now, our initial condition was that omega naught was equal to 0. It didn't have to be, but in this case we did that. It's possible to do this with an initial angular velocity, so that's not a necessary condition, but it was in this case, so we'll just strike it out. Now what I can do is substitute in the correct acceleration expression, which we got from dynamics. So v naught minus mu gt, and that will be equal to, and again I'm going to substitute in the correct expression for alpha. That's going to be 5 mu g over 2r times t, so the r cancels. So this is just 5 mu gt over 2. And then I can bring this mu gt back to the other side in order to factor out the t's, so that v naught will be equal to 5 halves mu gt plus another 2 halves is 7 halves, so it'll be 7 mu gt over 2, or solving for t will be equal to 2 v naught over 7 mu g. And this will be the time at which the ball will stop sliding and begin to roll without slipping. Now again, the velocity will have to have decreased to this point while the angular velocity increases, but I know this is exactly the amount of time it will take to do that because it satisfies the condition of rolling without slipping using the accelerations we found from correct expressions for dynamics for both these frames. Now all I need to do is take this time and plug it back into either kinematic equation so that I can determine at what velocity it will actually begin doing this. So if v then equals v naught plus at, then that's going to be v naught minus mu g, that's the acceleration, times 2 v naught over 7 mu g. That's the time it will take to do it. And then watch what happens. The mu g's cancel. So it's basically v naught minus 2/7 v naught leaves 5/7 v naught. So when this guy begins to roll without slipping, the final velocity will be 5/7 of whatever its original velocity is. Notice this is not a function of mu. So whether the bowling alley was particularly slick or whether the mu value changed as you went down the bowling alley wouldn't make any difference. All this takes is 5/7 of its initial velocity in order to reach its final velocity. Now what is true is if the mu value is larger, then of course the time it'll take less for it to reach this rolling without slipping, and if the mu value is smaller, it'll take longer. But what the final velocity is compared to the original one, notice, is no longer a function of mu. We can then do exactly the same thing with the rotational velocity if we want to. And that is that omega equals omega naught plus alpha t. Omega naught was 0, but alpha was 5 mu g over 2r. And of course t was 2 v naught over 7 mu g. And once again, the mu g's are going to cancel, and I'll end up with, the 2's are going to cancel, I'll end up with 5/7 of v naught over r. Now, we knew what that result was going to be anyway, only because we already knew what the linear velocity was, and by the time we get to this linear velocity, remember these guys are now in lockstep, which means omega should be v over r, And notice it is. The omega at that point is nothing more than the velocity that it has at that point divided by the radius. So this sort of verified it in two different ways, that these guys are definitely in lockstep now because this condition is met. This is arguably the most complicated of all the rotation problems because it involves linear dynamics, angular dynamics, linear kinematics, angular kinematics, the proper application of the condition for rolling without slipping, as well as solving two equations simultaneously. So again, try this with a couple of other different moments of inertia, and you'll see that the only difference really is what this factor turns out to be at the end. All right? Okay, armed with this, you should be sufficient to do tonight's quest. It is going to involve a few problems that involve rolling with slipping.